Welcome to this comprehensive video on the Laplace transform. In this lesson, we'll dive deep into this powerful mathematical tool that helps us solve differential equations and analyze dynamic systems. Let's start with a detailed definition. The Laplace transform takes a function f of t defined for t greater than or equal to 0 and transforms it into a function f of s in the complex domain. The transform is defined by this integral. F of s equals the Laplace transform of f of t, which equals the integral from 0 to infinity of e to the power of negative s times t, times f of t dt. Here, s is a complex number that can be written as sigma plus I omega, where sigma is the real part and omega is the imaginary part. Now, this improper integral doesn't always converge. It only converges for values of sigma, the real part of s, that are large enough to satisfy this condition. The integral from 0 to infinity of the absolute value of e to the power of negative sigma times t times f of t dt is finite. The set of all such values of s where the integral converges is called the region of convergence, or ROC. We often write that the Laplace transform is valid for the real part of s greater than sigma 0, where sigma 0 depends on how quickly f of t grows. Now, let's look at some common Laplace transform pairs and their regions of convergence. Here are 6 standard pairs of functions and their Laplace transforms. First, for the constant function f of t equals 1 for t greater than or equal to 0, the transform f of s equals 1 over s, and this is valid for the real part of s greater than 0. For f of t equals t to the power of n, where n is a non-negative integer, f of s equals n factorial divided by s to the power of n plus 1, valid for the real part of s greater than 0. For the exponential function, f of t equals e to the power of a times t, f of s equals 1 over s minus a, valid for the real part of s greater than a. For f of t equals sine of omega times t, f of s equals omega divided by s squared plus omega squared, valid for the real part of s greater than 0. For f of t equals cosine of omega times t, f of s equals s divided by s squared plus omega squared, valid for the real part of s greater than 0. Finally, for the unit step function at t equals c, f of s equals e to the power of negative c times s divided by s, valid for the real part of s greater than 0. Now, let's examine some key properties of the Laplace transform with explanations. Property 1, linearity. Because integrals distribute over sums and constant factors, we have the Laplace transform of a times f plus b times g equals a times f of s plus b times g of s. Property 2, differentiation in t. Using integration by parts, we can show that the Laplace transform of f prime of t equals s times f of s minus f of 0 plus. Property 3, multiplication by t. By differentiating under the integral sign with respect to s, we find the derivative of f of s equals negative Laplace transform of t times f of t. Therefore, the Laplace transform of t to the n times f of t equals negative 1 to the n times the nth derivative of f of s. Property 4, time shifting. If g of t equals f of t minus c times the unit step at t equals c, then the Laplace transform of g equals e to the power of negative s times c times f of s. Property 5, frequency shifting or exponential modulation. The Laplace transform of e to the power of a times t times f of t equals f of s minus a. Property 6, convolution. By definition, the convolution f star g of t equals the integral from 0 to t of f of tau times g of t minus tau d tau. Then, the Laplace transform of f star g equals f of s times g of s. Convolution in time becomes multiplication in s. Let's discuss 2 important theorems that help us quickly determine limiting values. The initial value theorem states that if f and f prime are Laplace transformable, then the limit of f of t as t approaches 0 plus equals the limit of s times f of s as s approaches infinity. Intuitively, this means we can find the initial value of a function by examining its Laplace transform at very high frequencies. The final value theorem states that if all poles of s times f of s lie in the left half of the complex plane, meaning the real part is less than 0, except possibly at s equals 0, then the limit of f of t as t approaches infinity equals the limit of s times f of s as s approaches 0 plus. This gives us a way to find the steady-state value of a function directly from its Laplace transform without inverse transformation. Finally, let's work through an illustrative example to see how to apply the properties we've learned. Let's find the Laplace transform of t times e to the power of 2t. Step 1. We know that the Laplace transform of t is 1 over s squared. Step 2. Now we apply the frequency shift property with a equals 2. For a function f of t, the Laplace transform of e to the power of, at times, f of t equals f of s minus a. So the Laplace transform of t times e to the power of 2t equals f of s minus 2, which equals 1 over the quantity s minus 2 squared. The region of convergence is the real part of s greater than 2, which comes from the requirement that the exponential term must converge. This example demonstrates how combining the standard transforms with the properties of the Laplace transform allows us to find transforms of more complex functions. In conclusion, the Laplace transform is a powerful mathematical tool with applications in differential equations, control systems, signal processing, and many other fields. We've covered the detailed definition, common transform pairs, key properties, important theorems, and worked through an example to demonstrate the application of these concepts. By understanding the Laplace transform and its properties, you can analyze complex systems and solve problems that would be difficult using other methods. Remember that the power of the Laplace transform lies in its ability to convert differential equations into algebraic equations, convolution into multiplication, and time shifting into exponential multiplication. Thank you for watching this comprehensive overview of the Laplace transform.